In this video, we are going to discuss Theorem 12, the ratio test. The ratio test is one of the most important tests used for testing the convergence of an infinite series. So let us consider a sequence AN where all the terms AN is positive. Now, how do you use the ratio test? It's actually very easy. First of all, you form the ratio of an plus 1 over an, and then you take the limit of index n's to infinity. What can you say about the ratio of an plus 1 over an? It is the ratio of the next term in the series and the terms an before it. If this ratio is, say, larger than 1, this means the an plus 1, the term that is next to an, is always larger than the term an. In the case where the ratio is less than 1, then what you can say is that an plus 1 is smaller than an. So you can imagine for the case where raw is larger than 1, it means the next term is always larger than the term before it. So imagine that this is the case for raw larger than 1. The term before it is always smaller than the term after it. Okay, so the term here is larger than the term before it. The size of the term here is larger than the size of the term before it. In the case where the ratio is less than 1, it simply means the term that is after an is always smaller. So if you start off the sequence of an from some initial value, then it will get smaller and smaller as n gets larger. In the case of raw larger than 1, where the terms in the series grows larger and larger, the chance for the sum to converge will become less likely. If you have a situation where the ratio raw is getting smaller and smaller when n is increasing, then there's a chance for the series to become convergent. For the ratio test, what you do is you take the limit of this ratio and calculate raw. There are three possibilities of raw. If raw is smaller than 1, it means the term in the series getting smaller and smaller, and therefore this would infer the series is convergent. If raw is larger than 1, it would infer the series is divergent. If raw is 1, then there's no conclusion can be made about the convergence of the series. The series could be divergent or could be convergent. Let us look at example 1a. To apply the ratio test to example 1a, what you do is to first identify the expressions of the terms an in the series, which is just 2n plus 5 over 3 power n. You form the limit of an plus 1 over an. Then you take the limit of the ratio to n tends towards infinity. So I'm going to write down the expression for an plus 1, where I'll just look at the expression of an and replace all the n by n plus 1. So this is what I'm going to do. I'll write down 2n plus 1 plus 5 over 3 n plus 1. So this is referring to the expression of a at n plus 1. Here I'm going to write down the expression for an in the denominator, where an is just 2 power n plus 5 over 3n. I'm going to write down the next line of the equations and start to perform some simple algebra to simplify the expressions of the ratio. In this case, I'm going to group 3 power n terms together. The other term is grouped in terms of 2 power n plus 1 plus 5 over 2 power n plus 5. This could be easily simplified. This will be just equal to 1 over 3. I'm going to pull out the factor of 2 power n from the numerator of this term. This is just the expression of this term. In the downstairs, I'll also pull out the factor of 2 power n, then the numerator will become this. With this, I'll be able to cancel off the 2 power n in the numerator and the denominator. So what is left is 2 plus 0 over 1 plus 0, because 5 over 2 power n will both go to 0 when n goes to infinity. Therefore, what I left is 3 over 2 as the limit of the ratio a at n plus 1 over an. Therefore, according to the ratio test, rho, which is smaller than 1, infer that the sum of the term an in the series is convergent. That is the solution to example 1a. Now, let us look at example 1b. Example 1b is slightly more complicated because it involves the expressions of factorial. That is, if you have an n plus 1 factorial, what it means is it is equals to n plus 1 multiplied with n factorial. This comes from the very simple fact that n factorial is defined to be n times n minus 1, n minus 2, and multiplied all the way up to 2 times 1. Say, for example, if you have 5 factorial, that will be 4 times 3 times 2 times 1. So if you have 6 factorial, that will be just equals to 6 times 5 factorial. So this is just a simple example of this equation. Here, I will identify the terms in the definite series to be just 2n factorial over n factorial n factorial. To apply the ratio test, I have to form the ratio of a at n plus 1 over an. These questions is a little bit tricky because you may get confused when you try to deal with the factorial term. So first of all, let us write down the a at n plus 1 term based on the expression of an. That is, I'll replace all the n by n plus 1. The whole thing is to be sitting inside the factorial. Then, instead of n factorial, I have n plus 1 factorial, n plus 1 factorial. So that completes the expressions for a at n plus 1. Now I'm going to write down the expression for an, which is simply equals to this term, 2n factorial, n factorial, n factorial. How would you go ahead to solve these equations? It should be actually very easy. So let us look at this particular case. How would you going to simplify this? 2n plus 1, the whole thing factorial. Let us open up the bracket. You get 2n plus 2 factorial, and this is just equals to 2n plus 1. n plus 2 factorial can be expressed as 2n plus 2 multiplied with factorial term, which is 1 less than 2n plus 2, which is 2n plus 1. Then you can further simplify the terms of 2n plus 1 factorial further to 2n plus 1 times 2n factorial. So that's how this term becomes reduced to this. Therefore, I'm going to write down this term in the numerator, which is 2n plus 2, 2n plus 1, multiplied with 2n, whole thing of factorial. Then downstairs, I will have n plus 1 factorial. n plus 1 factorial can be easily written as n plus 1 multiplied with n factorial. Therefore, this term becomes n plus 1 multiplied with n factorial. So is this term is to be written as n plus 1 multiplied with n factorial. So that is the simplification of this expression for a at n plus 1. Then I'm going to write down the expression of n factorial in green, and we have 2n factorial. So with this, the 2n factorial terms get cancelled off. Here you get cancelled off with 1n factorial. Here you get cancelled off with 1 factorial. Then you could arrive at a very simple expression of 2n plus 2, 2n plus 1 over n plus 1, n. Now you can take the limit of this ratio for n goes to infinity. As usual, to take the limit of n going to infinity for this expression, you always try to cast the expressions in terms of 1 over n. Therefore, I'm going to pull out the factor of n from both denominator and the numerator. Upstairs, I'm going to pull out n. When I pull out n from the factor 2n plus 2, what I'm left is 2 plus 2 over n. And for this term, when I pull out a factor of n, I'll get 2 plus 1 over n. Downstairs, I'm going to pull out n. What is left is 1 plus 1 over n. Then this term also contribute n times 1 plus 1 over n. So here you can see the cancellations of the n both in the numerator and the denominator. Then when you simplify it further, you get just these very simple expressions. In the limit n goes to infinity, these terms just goes to 0, and what is left is 2 and 2, which is just equals to 4. So I conclude the ratio of a at n plus 1 over an is just equals to 4 in the limit n goes to infinity. So this is the values of rho, which is definitely larger than 1. So according to the ratio test, the infinite series in example 1b is divergent. That finished up the discussion of the ratio test. To conclude, what you do in the ratio test is you form the ratio of a at n plus 1 over an given the expressions of the terms an in the infinite series. When you take the limit, you should arrive at some number of rho. And based on the numbers of rho, you can then tell whether the infinite series is divergent or convergent. The special case will occur when the rho turns out to have a limit of 1. In that case, then you cannot make any conclusion about the convergence or divergence of the series.